The process of modeling heat transfer that happens within solids has led us to the heat equation, has led us to the thermal circuit model, to the lumped capacitance model, which is super useful. It gives us a lot of meaningful information that we can use to model systems. But we've already run into a couple of snags whenever we try to model heat transfer that's happening within fluids, right? We've already seen that because we assume fluids inside of our models to be semi-infinite, that precludes us from being able to use the heat equation because we find that the standard assumptions that would apply to such a system don't really work. We don't have a systematic way of fixing it. And so what we want to address now is to talk about the so-called problem of convection, which is the difficulties that arise whenever we try to consider modeling heat transfer within liquids. And from the perspective, at least, of undergraduate heat transfer, the fact of the matter is that we don't. We basically just resign ourselves to saying, well, we're just going to have to treat them as being semi-infinite. And then the real physical question is trying to figure out what the H is between that semi-infinite fluid and whatever other object we're dealing with, whether it be a solid or another semi-infinite fluid. So, how can we show this issue? Suppose that we went and created this relatively silly experiment. We take two, square rocks, one which has a top temperature T1 and the other has a bottom temperature T2. And, they have material properties. We can say that this, has some constant K1 and K2 and CP1 and CP2 and rho 1 and rho 2. It has all of the properties that we need, right? We know the surface area, we know the thickness, whatever. And we launch these things at a constant velocity v, such that both of these rocks stay together, right? So like that this configuration of the rocks doesn't change as these things are like hurtling through the air or space or whatever. As a result, what happens? Well, both of these rocks now have a kinetic energy, right? 1/2 times the mass times the velocity squared of each of these rocks. So we can define a kinetic energy that's associated with either object. We can also, of course, define a thermal energy. I mean, we did before, right? We had approximated very, very roughly that the thermal energy of an object, at least from the perspective of this course, was something like Cp rho times the volume times the temperature. More rigorously, of course, this would be a function of all kinds of other things like chemically and fluid mechanically and thermodynamically. There would be a whole lot of factors that would show up. But from the perspective of this course, the only thing that actually matters, the only thing that we actually try to change is this, right? The temperature and by extension, this thermal energy proxy. And if we try to do an energy balance around this system, right, we have to consider how the rate of change of this system's energy is affected by the amount of energy that flows in or out, plus the amount of energy that's being generated. Okay? And so I can consider it for either, the two boxes, or I can consider it for either of the boxes. But every single time that we've been doing this, the only energy that we care about is the thermal energy, whatever that expression is. The only thing that we've ever done has been to say, well, this rate of change, the only thing that's changing is the thermal energy. And so I can directly relate changes of temperature in time to flows of thermal energy in or out of the boundary and how much is being generated. The velocity, the kinetic energy of these two objects never factors in to this sort of analysis, right? And the reason for that is because we assume that the kinetic energy plays no role in the thermal development of the object. That even if the kinetic energy were to change over time, that change in the kinetic energy is completely decoupled to the thermal energy changes. And that, all of the stuff that involves changes in the kinetic energy is mechanical, right? It's like the ballistic motion of the stuff. Who cares about that, right? We're studying heat transfer. All we care about are temperature differences. And this is a pretty good assumption to make whenever your objects have negligible kinetic energy. But if, instead of considering this sort of system, What if instead we generated an experiment where we had a block that was sliding on the ground with some velocity v and some initial temperature T, and all of the material properties that you would need, right? As this thing slides forward, friction is going to cause this block to come to rest. And so what happened to all that kinetic energy? It gets converted into thermal energy. Thermal energy that increases the temperature of the bottom surface of this block, and which also increases, hypothetically speaking, the temperature of the air immediately surrounding the block, just as a result of like viscous interactions between the block and the air. In that situation, we can't decouple the kinetic energy of the block from its thermal energy, because there is a process that is occurring, a frictional process, that is converting mechanical energy into thermal energy. And so as a result, we can't just write an equation that balances out the energy of the system while ignoring all of the generation and the flow and all of the characteristics of the mechanical components of the system. The mechanical and thermal parts are now intertwined. And the problem is, right, that we had derived the heat equation by assuming that this change in the energy of the system was entirely based off of changes in the thermal energy. Adding the changes to the kinetic energy, whatever those may be, and all of the terms over here result in an equation that is either going to be too specific for, general use, or too complicated to be able to deploy at an undergraduate level heat transfer course. What's one example of this? Well, here's a silly one. Right, once again, suppose we have the block with temperature T moving at velocity v, and that everything else is just, like empty. Neglect the energy of the air surrounding this stuff. And suppose that I try to do an energy balance around this empty region of space. This energy balance should be trivial, should be zero, right? Because this is the rate of change of the thermal energy of empty space, which should be nothing, right? The density is zero, so everything's zero. There's no flow of energy going in or out, and there's no thermal energy generation. But what happens as this block starts to slide forward and then eventually enter into this region, right? As it enters, this block has, as far as we know, a thermal energy which we have described as being this. And that thermal energy is now flowing into the boundaries of this region of space, not because of a heat flux, right? Not necessarily because of the fact that that energy is moving in as a result of a temperature difference or a thermal gradient. It's moving in there because there's a non-trivial velocity that is literally moving the matter with this thermal energy into the volume. And that is not something that we ever modeled. We never talked about heat transfer as modeled, not necessarily via temperature differences, but as something that happens literally because you're taking mass that has a temperature and moving it into a region of space. So this generates a big complicating factor in the formulation of the equations, because we could derive an expression for this, but we haven't, right? We haven't, throughout the process of defining what heat transfer rates or heat fluxes are, we've never considered this scenario, never analyzed the system where this occurs. The other complication that results, the other thing which happens, this one's a little bit more esoteric, but just like how we said that mechanical energy can be converted into thermal energy, it actually turns out that thermal energy can be converted into mechanical energy too. Here's an example that we're going to dwell on a little bit more later, but for now, let's just take a quick look at it. So suppose that I had some liquid bath. Okay, so this is water. And I have some kind of radiator or heater over here that is injecting heat and raising the temperature of the right-hand side of this bath. Okay, so we can just say that there's like a Q here. Or alternatively, we can model this side of the bath as a thermostat, where we say that there's some temperature on the right TR, and that over here, maybe we'll say that there's a temperature TL, and then we'll say that this has a temperature TB, and this has a temperature TT. So like top, bottom, left, and right. And then we have this thermostat, which makes it such that the temperature on the right is larger than everything else, right? So this temperature is larger than all these other temperatures. And you can either assume that these temperatures are the same. Maybe if you want to, you can assume that, TL is maybe smaller than TT and TB. It's up to you. The physical phenomena that's going to occur is technically independent of these things, or at least the magnitude is dependent, but the fact that it occurs is independent. So you have this liquid. It starts off at being the constant temperature everywhere, like the same temperature everywhere. And then slowly but surely, the temperature of this right-hand side increases, right? The temperature of the liquid over here increases. And what occurs, and this is from thermodynamics, not from the study of heat transfer, what occurs is that as the temperature of a fluid increases, usually its density decreases. And so what you create is a little pocket right here of liquid that has some low density relative to the regular density of the rest of the liquid. Because this density is lower, buoyancy starts to take hold, right? This patch of liquid behaves like it's basically a submerged object that has a lower density than the background density of the liquid. And so as a result, it starts to rise up, just like any other object which is buoyant. And so you start to observe that the liquid flows upwards. This little hot patch of liquid flows upward. In order to prevent a vacuum from developing, of course, then liquid that is over here at the bottom has to be pulled in over to the side to make sure that you don't get cavitation or, this doesn't generate a vacuum. As it goes upwards, it has nowhere to go, right? It can't go further upwards than the surface, but it still has that kinetic energy. And that kinetic energy, some of it is lost to viscous effects, but in general, what it'll do is it'll carry the liquid along the surface in this direction until it eventually reaches, this other region, which is far away from this thermostat, right, from this high temperature. And as that temperature starts to settle down, right, as the temperature of the chunk of fluid that's been flowing around the system starts to go back down to a background temperature, or if you assume that this temperature TL is lower than the background, then it starts to become lower. Eventually what happens is that buoyancy effect starts to go away, right? And so the liquid starts to settle down and will, in general, start to flow downwards, okay? If this temperature is the same as the background temperature, then it'll kind of spread out, but the general trend is more or less the same. And the reason the general trend is more or less the same is because now that the liquid's at the bottom, it gets kind of entrapped by the current that's been developed by the rising liquid on the other side, right? Because as this thing goes down, there's a fresh batch of liquid that's moving upwards, that's dragging everything behind it. And so what starts to happen is the development of what is usually called a convection current, which is happening as a result of the fact that there is a continuous temperature gradient between this side of the wall and the other walls, right? Because there's a continuous temperature difference, like continuous in time, because there's that temperature difference that's happening on the edges of these walls, there is, of course, heat transfer that's occurring, right? Heat has to be injected into this liquid in order to heat it up and alter its density. But then buoyancy is converting that change in the thermal energy of the liquid here into a change of its mechanical energy that we can observe, not just at scales that, are relevant to like a fish tank, but also atmospherically. One of the key things that drives the motion of air in weather events is the fact that there's imbalances in temperature. And those imbalances in temperature cause the motion of the air inside of those weather events, hurricanes, cyclones, tornadoes, to either strengthen or decay, depending on the physics. And the point of what I'm trying to say is that not only do we have that mechanical energy can be converted into thermal energy, but we also have situations where thermal energy can be converted into mechanical. It's not just one way, which makes it so difficult to model these systems. Great for a person who has a career modeling them. And so what's the last thing that I want to say before we actually start tackling individual specific systems? Well, there's a way that we can model, or a way that we can distinguish two different kinds of systems, not just based on the complexity of modeling them, but also on how we can assume that that coupling between the mechanical and the thermal energy is generated, okay? One convective scenario, which is by far the most commonly studied because it's the most simple, is the notion of forced convection. And in the notion of forced convection, the idea is that the kinetic energy influences the thermal energy. That is to say, that the flow of the fluid affects how thermal energy is being transferred, but the flow of thermal energy does not affect the flow of the fluid. That is to say, in the language of this sort of thing, we assume that it's a one-way coupling, okay? That the kinetic energy of a piece of fluid will affect its thermal energy and how that thermal energy becomes transferred, right? But that the transfer of thermal energy is not going to affect the kinetic energy of the fluid. And you can imagine that this could be something that occurs if you have a particular external forcing that dominates the behavior of the system. So for example, if you have something like a really powerful fan, right, that's just blowing air, the convective effects as a result of buoyancy because of temperature imbalances are going to be completely dominated by the fact that you have an industrial fan that's blowing things around. And so because it's usually externally forced, because the flows are usually externally forced in those situations, we call that forced convection. But really, it's just a representation of this coupling. And then, of course, we have what's called a free convection. Free convection because the liquid can kind of do whatever it wants. There's no external thing that's making it flow in a specific way. And in this scenario, we do, in fact, have that two-way coupling where the kinetic energy can influence the thermal energy and the thermal energy can influence the kinetic energy. And so the first one that we're going to try to tackle, because of its simplicity, is the forced convective case. And we're only going to talk about free convection qualitatively, because it turns out that the experiments that are required in order to, get meaningful information for how to model these systems are so complex, and the data that we get is so scarce and, tricky to deal with, that forced convection actually is much more, not just easy, but more accurate, at least as accurate as it can get when it comes to talking about convective heat transfer, okay? And so forced convection will be what we talk about next.